Everyone, my name is James Faulkner, Product Marketing Director in the Red Hat Application Services Business Unit here at Red Hat, and I'm joined by Arnal Dayaratna, Research Director of Software Development at IDC. So today we'd like to share with you a bit more about what Quarkus is and some key results from a recent report Red Hat published with IDC that outlines the technical and business benefits of Quarkus. So if you're not familiar with Quarkus, it's a Java application framework optimized for building microservices and serverless applications that are containerized and run on platforms like Kubernetes and Red Hat OpenShift. It's targeted primarily at net new greenfield application development, but also for Java developers who are using things like Spring Boot and MicroProfile to build microservices today. So aside from the framework itself, Quarkus features a lot of developer productivity enhancements like live coding, remote development, and integration with IDEs like Eclipse, IntelliJ, and others. So Quarkus is Java, which has really been very popular for solving complex business challenges of scale, flexibility, reliability. So those millions of Java developers that are out there today that have been using it for 2 decades will be able to easily start using it. And as you'll see in a moment, Quarkus's stunning performance characteristics, it really represents a generational leap in Java by reimagining how Java apps are built for the cloud. And finally, with over 300 Quarkus extensions available today to connect to your existing systems, Quarkus can really provide immediate business benefit and long-term value for your Java application landscape. So I'll turn it over to Arnal today to talk more about the report. Arnal?
Thanks, James. So, as James mentioned, Quarkus is a Kubernetes-native Java framework, and what's notable about it is that it optimizes Java for containers, Kubernetes, the cloud, and serverless environments. So why is this important? It's important because historically, increased adoption of containers has posed a challenge for Java because containers deliver the portability that was previously provided by the Java virtual machine, more commonly known as the JVM. JVMs running inside containers represent an extraneous infrastructure that brings operational inefficiencies to the performance of container-based Java applications. Java applications deployed on containers are notorious for large memory requirements and lengthy startup times. Quarkus optimizes Java for containers by enabling faster startup time, lowered memory usage, increased deployment density, improved scaling, improved developer productivity, and even cost savings, as we'll see. By way of methodology, we empirically measured the benefits of using Quarkus in comparison to a non-Quarkus Java application that was developed using another widely used Java development framework. The other Java development framework in question was Spring Boot, although in this document we refer to it as Framework A. The comparison of Quarkus to a non-Quarkus Java application, as you can see here, featured 3 application types, namely Quarkus on JVM, Quarkus native, and Framework A. It's worth noting that no optimizations to Java were made for the purpose of these measurements. All heap memory settings are equivalent for Quarkus on JVM, Quarkus native, and Framework A. And these comparisons between a Quarkus and non-Quarkus Java application focus primarily on application-related costs. We measured cost savings by quantifying the number of nodes dedicated to workloads for Quarkus and non-Quarkus-based Java applications. Speaking of cost savings, as discussed earlier, benefits of using Quarkus include reduced startup memory, reduced memory utilization, increased deployment density, faster startup time, and improved scaling. These benefits translate into cost savings for cloud resource consumption on the order of 37% for Quarkus on JVM, and 64% for Quarkus Native. This means that if you spend $100,000 annually in memory consumption on AWS using Framework A, you would in fact spend $63,000 with Quarkus on JVM and $36,000 for Quarkus Native. The next set of slides examines some of the findings that we found regarding Quarkus performance, starting with the topic of startup memory. Our first set of findings quantified the startup memory of a Quarkus application in comparison to a Framework A application for containers running on a bare metal environment. On-premises startup memory usage of Quarkus on JVM and natively was lower than Framework A, as shown in the chart on the left in the orange segments. Specifically, Quarkus Native reduced memory usage by roughly 90% in comparison to Framework A, and Quarkus on JVM reduced memory usage by roughly 20% in comparison to Framework A. Why is this important? It's important because traditional cloud-native development stacks that are based on the JVM have large memory footprints and slow startup times. As such, lower startup memory is important because it indicates the amount of memory that an application that is not under heavy load will use in a production environment. In cases where the consumption of memory is used to calculate cost, customers will pay less in cloud resource consumption using Quarkus than they would for Framework A. So to summarize, this reduction of startup memory on the part of Quarkus is illustrative of how Quarkus optimizes resource consumption with respect to memory and subsequently enables memory-related cost savings. Continuing with the topic of the optimization of memory consumption, our second set of findings quantified how Quarkus reduces not only startup memory, but memory utilization more generally, this time for 10 Kubernetes pods on OpenShift 4.2 on AWS. And the finding was that the memory utilization of Quarkus was 1/8 that of Framework A for Quarkus Native, and roughly 2/3 that of Framework A for Quarkus on JVM. What's the significance of this? The significance is that Quarkus optimizes resource consumption with respect to memory and subsequently enables cost savings related to memory consumption, as we've seen before, but moreover, reduced consumption of memory by a Kubernetes application translates into an increased likelihood that the application will successfully run using Kubernetes as enabled by Quarkus. Turning to the topic of Quarkus and its impact on deployment density. This slide quantifies the number of pods that can be started on OpenShift 4.2 hosted by AWS given 2 gigs of memory. The finding here is that the number of pods that can be started with Quarkus is greater than Framework A as follows. In the case of Quarkus on JVM, in the middle of the chart on the top left, there's an increase of approximately 1.5x with respect to the number of pods that can be started. And for Quarkus Native, there's a corresponding increase of 8x, so an 8-fold increase. These findings illustrate that Quarkus users can do more with the same amount of resources. And this means applications using Quarkus can be deployed on fewer nodes than applications that don't use Quarkus. And the reduction in the number of nodes means that organizations can leverage fewer infrastructure resources to accomplish the same goals. This reduced use of infrastructure resources enables organizations to save money and also simplifies the management of the resources in question. This slide quantifies the extent to which Quarkus-based applications can be scaled up. And the findings here focus on the ability of an application to scale up by quantifying the time it took for a pod to register itself as ready after initialization. The relevant deployment environment was on premises and featured containers on bare metal. And the key findings were that the median Quarkus JVM time to scale up was roughly 60% of the time for Framework A. Meanwhile, Quarkus native time to scale up was roughly 20% of the time required for Framework A. So there are corresponding performance improvements of 40% and 80% respectively. So once again, let's ask the question of why is this significant? This is notable because a single cluster can often be used for many applications, and as a result, the ability of an application to scale up is illustrative of the ease with which a cluster can be used for many applications in parallel. Quarkus on JVM and Quarkus native demonstrated the ability to scale up faster than Framework A. The speed with which Quarkus enables containers to scale up means that services can be scaled down when not utilized to optimize resource consumption. Furthermore, the ability of Quarkus to rapidly scale up individual services enhances the freedom of developers to develop applications with microservices architectures that distribute services amongst a multitude of individual containers that differentially scale up and down. Turning to the topic of startup time as measured by time to first response, this lab measured the startup time of a Quarkus application in comparison to a Framework A application for two deployment environments, namely containers on bare metal and a serverless environment. In the case of containers on bare metal, we saw improvements in startup time for Quarkus native on the order of 8.6%, and for Quarkus on JVM on the order of 46% in comparison to Framework A. And meanwhile, in the case of a serverless environment on OpenShift 4.2, the median Quarkus JVM startup time was roughly 48% of the time required for Framework A, and the Quarkus native time with respect to startup was 23% of the time required for Framework A. So Quarkus native didn't perform quite as well as it did in a serverless environment when compared to the containers on bare metal environment. So why is this important? It's important because one of the key benefits of containers as compared to virtual machines is, in fact, their reduced startup time. In the case of Java applications, startup time for container-based applications tends to be longer than other applications because of the overhead introduced by JVMs running on container infrastructure. Because container-based applications are notorious for lengthy startup times, improvements to these startup times constitute a notable performance-related benefit. For serverless infrastructures, reduced startup time is especially important because containers are created on demand, and the time to first response can impact user experience. Reductions in startup time for container-native serverless applications translate to lower application latency, and improve performance. In the case of functions as a service-based applications, for example, reduced startup time means faster execution of an application subsequent to the realization of a predefined event or trigger. This lab examined developer productivity and is the first of 3 labs that examine that topic as enabled by Quarkus in comparison to Framework A. And specifically, the slide illustrates the quantification of the number of operational steps required to update an application. Specifically, the lab examined the number of operational steps associated with adding extensions to Quarkus Maven projects. As you can see in the box in purple, Quarkus requires 2 steps to update applications in the form of editing an application and saving it. In contrast, frameworks such as Framework A require developers to make a change to a project, stop and start relevant services or applications, test that change, run the application, and then test the application again. This means that Quarkus radically reduces the number of operational steps required by developers to update an application and thereby enhances developer productivity. This slide examines Quarkus's contribution to developer productivity in the context of an application that uses Kafka-based streaming data. And the finding here is that by using Quarkus, developers can reduce the number of operational steps required to update a Kafka-based application. So it's a very similar finding to the finding that we saw in the previous slide for a slightly different use case. Whereas traditional Java frameworks such as Framework A require developers to stop and restart a Kafka server to understand the efficacy of application-related updates, Quarkus users can make application changes and save them without performing additional operational steps. So there's no need for Quarkus users to stop the Kafka server, rebuild the application, restart it, and check if changes are working. Once again, it's simply the case that developers using Quarkus can change code, as in make edits to code and save it. So why is this important? It's important because Quarkus brings the power of live coding to streaming Kafka-based workflows. And this means that developers can make changes to applications that leverage streaming workflows without having to restart either the application or the workflow. And this ability, namely the ability to make live changes to an application that uses streaming data, once again enhances developer productivity by reducing the number of operational steps required to update an application. Our final lab examines the ability to program using both imperative and reactive approaches to programming within the same source file in a project and make live changes. And the key finding here is that Quarkus empowers developers to create applications that feature the conjunction of reactive and imperative programming, thereby obviating the need to maintain discrete projects for 2 different styles of programming. This centralization of the capability to develop imperatively and reactively renders it easier for developers to switch between the two programming modalities as needed within the same source file, without resorting to separate development environments or the creation of separate projects or sets of files. So given that, I'd like to turn it back to James.
All right, thank you, Arnaud. So a lot of what Arnaud discussed was summarizing what we found in the lab validation. If you want to read the full lab validation, including this getting access to the hardware and software specifications and source code that we used for these findings, you can visit the URLs you see here on the left. If you want to actually try Quarkus and get hands-on today without installing anything 100% directly in your browser, you can head over to the URL in the middle of the screen here and run through a series of exercises that really showcase some of the things that Arnaud discussed earlier in the previous slides. And then lastly, if you just want more information or want to generate projects for your own use and really see how Quarkus can fit into your existing Java and new Java landscape, head over to quarkus.io or code.quarkus.io and get started today. So these are a couple of good resources for you to continue your journey if you want to learn more about Quarkus and what business and technical benefits it can bring for you and your company. So I want to thank you again for attending and watching this presentation, and we hope you learned a little bit more about Quarkus and got some more resources that you can use. So thank you very much. All right. Hello, everyone. Thanks again. This is Faulkner here, live with you. Also, Arnaud is also on the line here. We want to answer some of the questions that we see that you submitted. We see a ton of questions. I tried to answer some of them while Arnaud was doing presentation, but couldn't get to all of them. There's a ton of them, so awesome job. So I'm gonna pass it back to Arnaud to answer a question we received about cost savings for more complex apps. So Arnaud, do you want to address that one?
Sure. So I think the question is there a correlation between the cost savings that we've seen in the findings that are illustrated in this presentation and more complex apps? In other words, as applications become more complex and leverage more microservices, for example, and more resources, is it the case that the cost savings similarly changes in a linear fashion to the complexity of the application? And what I can say, first of all, is that it's extremely rare that operationally the costs involved in running a more complex application scale in a linear fashion in correspondence with the complexity of the application. So that's the first point. Second, that having been said, it does, it is worth noting that the cost savings that are realized through the use of Quarkus in comparison to Framework A, as it's called, whether it's Quarkus on JVM or Quarkus native, but likely do not scale in a completely linear fashion, but they certainly do rise in conjunction with the associated increase in the complexity of an application. James, did you want to add anything to that?
Nope, I think that's fantastic. Yeah, you definitely will see a rise, but it's not sort of linear with the size or the footprint. That's one of the trade-offs Quarkus makes. In fact, that leads me to another question asked was around does it make sense to start by going to Quarkus on JVM and then as a next step going to Quarkus native? So the answer is that's certainly an option. Quarkus on native, and I'll answer another question at the same time. So what Quarkus on native does is it does do compile time optimization. So it does dead code elimination, where it examines all the code paths that could possibly be taken by the app and then eliminates any code and libraries and stuff that will never be visited to make it smaller. Quarkus also, even before that occurs, does framework optimizations, and this is key to one of the Quarkus was created, was that we do a lot of optimization VM level, so garbage collectors or just-in-time compilation techniques, but none of those address the frameworks that are built and used on top of the JVM for developers. So Quarkus, what it does at build time is it essentially sort of boots up the app, if you will, let frameworks do their initialization and dynamic relocations and whatnot, and then saves that state. It's not a memory capture, it's basically a high-performance index of linkages between things, injected code, and so that at runtime it can start up very fast and not take up the end CPU or the memory and time required, which you don't get back for doing those framework optimizations. So that's one of the big differences and one of the big trade-offs that Quarkus makes. It's really designed for environments in which you need fast and small, but you also don't need the dynamic behavior of traditional frameworks like Spring Boot, which incidentally is the framework A in this lab validation study. But you need dynamic behaviors because you're on a Kubernetes, you're deploying an immutable architecture. If you need to replace or do a dynamic change, you simply rebuild the container and deploy it on top of the old one. So this is the cattle versus pets analogy. So Quarkus is designed to make different trade-offs that traditional Java has in order to optimize and get this stunning performance and really match the characteristics of how we deploy apps today. So that's kind of the impetus for Quarkus. So I think I answered a couple of questions that I wanted to ask that I saw asked. There's a ton of questions. We're not going to get to them all today. So I recommend Quarkus has a community. If you go to quarkus.io, there are chat rooms, there are mailing lists that you can ask technical questions of Quarkus. So be sure if you want to ask those kinds of questions, we can answer them. We probably don't have time today. So let's see. Arnold, you want to take another one? There's one about more details on the serverless environments and can Quarkus be used in serverless environments?
Sure. So the answer is Quarkus can absolutely be used in serverless environments. In fact, it boasts a multitude of benefits for serverless environments, and so those benefits are twofold. One, for serverless infrastructures, reduced startup time is important, because containers are created on demand, and so the time to first response can have an effect on user experience. And so what this means is that reductions in startup time for container-native serverless applications translate to lower application latency and improved performance fundamentally. In the case of functions as a service-based applications, for example, reduced startup time translates into faster execution of an application subsequent to the realization of a predefined event or trigger, whether it's a hashtag in a Twitter feed or some other kind of event. The other thing I think that's worth noting in the context of a conversation about Quarkus and its relevance for serverless is that Quarkus has a number of abstractions that facilitate the use of popular serverless development frameworks such as Lambda and Google Cloud Functions and many others. And this is extremely important because it increases developer productivity and enriches the developer experience with respect to the use of Quarkus for the development of serverless functions and applications.
Okay, awesome. Thank you, Arnaud, for that. Another question is, what about if I want to use Quarkus for Spring Boot? How effective is it compared to using only Spring Boot? So there's a longer answer behind that, but one of the things that Quarkus does is it Spring API compatibility layer. What this means is that if you're a Spring Boot developer today, it's very easy to get started with Quarkus because we have the exact same set of APIs for a number of Spring frameworks like Spring Web or Spring Security or a few others. Actually, I think there's 10 others now. And so those APIs, if you use those, familiar with them, those get dynamically translated to Quarkus APIs and Quarkus functionality. So we're not bringing Spring Boot into Quarkus. It's more like the familiarity boot allows you to use Quarkus. Hopefully benefits the value proposition of Quarkus as a Kubernetes Java framework, and then continue to use Quarkus going forward. So, but we definitely fully expect Quarkus and Spring Boot to live sort of side by side. Of course, they're separate Java frameworks, but we do have that compatibility layer within Quarkus so that you can use your Spring framework familiarity, and you can still get the value out of Quarkus, and so you use that knowledge. Yeah. So let's see, I think we have time for one more question. Yeah, there's a question around migration. Is there a plan to migrate existing Spring Boot apps to Quarkus? So one part of that answer is the CI compatibility that I mentioned. We also have a tool that we have used in the past called Windup, and this is a productized tool it's called a Red Hat migration toolkit for applications, and it examines your source code and then provides guidance on how to do this migration, because almost all of our customers and many of you probably have existing apps and you're wondering if Quarkus, what would it mean to use Quarkus for existing applications. So we have this toolkit that will examine your source code and then tell you what the equivalence API is for doing that migration, or provide additional documentation links and other material to help you in that migration. It also assigns a level of difficulty, so you can run it against 100 apps and it will kind of rank which apps are going to be more difficult to migrate. So it's a very powerful tool that we use with our customers to migrate. It is available. It is an open source project, and then for developer support in a corporate setting, we have the Red Hat Migration Toolkit for Apps. So the new version of that is 5.1. It's out in early December, and it will have a full set of rules for doing Spring Boot to Quarkus migrations. So I think we're done. I think we're out of time. So I want to thank everyone again for attending today. We saw a ton more questions. I'll talk with our team and see how we want to publish those. We might just add them to the Quarkus FAQ. There's several of these are really good I haven't seen before, so thank you very much for that. And again, thank you, and Arnal and I really appreciate you taking the time to attend this, and hopefully you can follow up with some of the resources that we showed at the end. So Arnal, you want to say any closing words?